So in today's lesson, we're going to be talking about shadows. And this is going to follow on from our last lesson where we learned about light. And so just to recap quickly, let's recreate our example we kept on using, which was this table that was lit from above. And so basically what we talked about last time was we came up with a formula, a way to model this, where if we wanted to figure out whether any point on this surface was being lit, we would look at its surface normal and we'd compare that surface normal to the vector that points to the light. And so basically, if these are aligned to some degree, then the surface will be lit. And if they're not aligned, meaning that there's basically greater than or equal to 90-degree difference between the two vectors, it will be in shadow. Okay, so we had that type of shadow already in our model. Now what we did not have though is cast shadows. So let's look at what happens if we have like a floor in this scene. And we did talk about this a little bit when it comes to indirect light, but what we didn't talk about was direct light. What happens with direct light is that the light shines down, it lights this tabletop. Okay, we covered that. But then what about the floor? Is that there will be a cast shadow here that's caused by the table blocking this floor. Okay, so that's going to be in shadow, but if you notice, right, it still is going to be pointing up as far as the surface normal goes, and then it's still going to be pointing towards the light in a way that's aligned with the surface normal. So this should be lit according to our model, but we know it's not because it's in this cast shadow area. So let's see if we can make an adjustment to our lighting function. So our lit amount is going to equal our alignment function, right, between our surface normal and the vector that points to the light. So we drew those as N and L. Okay, so what we can do is we can take this light amount, and after we calculate that, we can then multiply in like a mask. And this mask, we'll call it the shadow mask. And basically what this is going to do is that if the area is inside of a cast shadow, then this shadow mask will be 0, right? Or if it's not in a cast shadow, it will be 1. And so that will kind of preserve our lit amount if we're not inside of a cast shadow, and it will kind of cancel out the lit amount and will go into shadow if there's a cast shadow, if there's another object blocking this. Okay, well, but how do we calculate this shadow mask, right? That's kind of the hard part of this, because we can't just look at our whole scene and start doing like physics queries into our scene to see whether something else is blocking a vertex on the floor, because let's review actually our whiteboard image from the second lesson, because I think we may come back to it a few times in this lesson actually. So let's just open up our whiteboard image from the second lesson. Let's come down to the part where we talked about shaders. We're doing this batch processing where we're feeding each vertex in independently. And so the vertex is not going to be able to look at the whole scene. It's just looking at that particular vertex. And it does have access to like shader globals like we saw last time, like light direction and light color and things like that. But it's not going to be able to look at all the other vertices in the scene or anything close to that. It's going to need to be a very simple program that can run in parallel across all this different data. So how are we going to determine the shadow mask? Well, let's go over a couple of different techniques, and let's start with a kind of typical way that this would be done in a real-time context, is that we could use something called shadow mapping. And you could think of this technique as being applied in 2 different steps. Okay, so step 1 and step 2. And let's first say what step 2 is, because it's going to be more familiar to us. So we'll call this like the main render pass. So we're going to just render our scene like normal here with one adjustment, which is that we're going to be doing this shadow mask as part of our main render. But otherwise, it's going to be identical to what we already have. And this is going to be, sending our scene through the graphics pipeline, like we saw in our lesson 2. The graphics pipeline is sending it through this whole thing to the pixel shader, which then outputs to our device screen. So let's put here that we're going to output to our laptop screen at the end of our main render pass. Now, by putting that there, it kind of suggests we're not going to do that in step 1, right? So in step 1, we're going to do the shadow map pass. And this is not going to go to the device screen. We're still going to be going to a picture plane that has pixels. So we're still going through the whole graphics pipeline with some adjustments, but it's going to target a texture or a map that's going to be basically just inside of the computer's memory. It's not going to be displayed on the screen, and we can just maybe draw some shapes here to show that this is like an abstract object that lives inside the computer's memory, but we're not actually seeing it. Okay, so that's our shadow map. Now, why did I say shadow mappings? I don't know what I was thinking about there, so let's delete that. Okay. Let's move on now. So let's break down these steps a little bit. So what happens inside of this shadow map pass? Okay, we'll just add the word pass here. And what we're going to do is, again, come back to our lesson 2, and let's copy this over. And we'll see how this is going to change for our shadow map pass. So we've already seen, right, this is going to go away, and it's going to be replaced by this shadow map at the end of this process. We're still going into a picture plane, but we're going into not the device pixels, but the pixels of the shadow map. Okay, the other thing that's going to change is that we're still going to use a camera, but I'm going to take that away, and I'm going to draw a light here instead, because we're still going to use a camera, but we're not going to use the camera that we used during the main render. We're going to use a different camera that's positioned and oriented like the light. So we're going to render this whole scene from the light's perspective. And then what we're also going to do is, rather than outputting like the color that we'll see in the main render, we're going to output to a encoded depth. And so this encoded depth we can use basically to recreate like a 3D position that this light is seeing, because we have a projection that's going into 2D space, and if we draw the depth as like this encoded grayscale value, we can then like recreate a 3D position that the light's seeing. If you think about it, if anything that shows up on this map, if it's seen by the light, or if it's seen by a camera that's in the light's perspective, that means that light will be hitting whatever object is shown on this texture. And you may think, well, what's the big deal? Because we already know what's being lit. Well, think about it this way. If it's seeing this table, it's not going to be seeing this floor that's behind the table. So that's different. It's only going to be basically rendering that table to this map. Okay, so then what do we do with that encoded depth? Now we're going to go into our main render pass. And this is where we're going to try to do this calculation. So let's pull that down. So now how are we going to calculate this shadow mask? What we're going to do is we're going to take whatever vertex is we're trying to light here, and we can duplicate this same transformation that we did in the shadow map pass to get our vertex into this projected space of the shadow map. And so we can sample the color value, which is basically the encoded depth, from this texture by using the projected XY position of our vertex here that we're trying to figure out whether it's lit or not. And then what we can also do is get the encoded depth value essentially of the vertex we're trying to light and compare that to what was actually rendered here. And if that's a different value, it means that the object that we're trying to light currently, if it's not being shown on this map, it means that it must be behind whatever's on that map. And so we can use that to create this shadow mask. So let me try to draw an example to show what would happen in our test scene here. So let's extend this out so I can draw it next to our current diagram. And let's zoom back in. So what I'm thinking we would see is we would have some kind of map that's rendered of the scene from this light's perspective. And so we'd use maybe like a darker gray color to show this floor, the depth at which it's seeing this floor. And then we'll have a brighter color where the table is, because it's closer to the camera that's rendering the light's perspective. And then we'll fill that in. So that's kind of what that map would look like, okay? And then if we're trying to figure out, let's say, a vertex that's located here, if we're trying to figure out whether that's in the cast shadow or not, if we're trying to determine the shadow mask value, what we would need to do is find where is this located on this map. And it would probably be somewhere like that, okay? And we could just determine, well, doing this transformation that we did here, what would be the depth that this point should have, and it would be kind of this gray color. And then we can compare that and see, well, it's actually this white color. So that means that this point here that we're trying to render is going to be inside of a cast shadow. Okay, so that's great. That's kind of how shadow mapping works. Now, there are some drawbacks to this, and as I kind of hinted at the beginning of this, we're not going to actually do shadow mapping today. So one of the issues with this shadow mapping is it's kind of complex. I mean, look at this. You have to add a second pass to your whole system. So I'll say complexity. But I didn't even get into all the complexity that would be required here because this is a point light, remember? And I just drew this from this orientation looking down at this object of interest. But if you've got objects that are all around this point light, that means you're going to have to actually, to do this correctly, you're going to have to actually do one map kind of like this way. And then you're going to have to do another map this way, and this way, and this way. And you're going to have to actually create a cube map, which is basically 6 maps that are, trying to capture the whole area around that point light. And so that's kind of a big drawback, especially for point lights, and not only for complexity, just implementation, but also for efficiency and performance and things like that, because you're going to have to render the whole scene 6 times in addition to your main render. Now, along that line of the performance, another big issue with this is fill rate, because, and what is fill rate? That refers to filling all these pixels of the output. There are going to be tons of pixels that we're filling through this graphics pipeline. And let's come back to lesson 2 again. So we'll see not only in the pixel shader, but also in this rasterization phase, we're just pumping out a lot of pixels out of this graphics pipeline. And that's going to be hugely multiplied for this shadow map. And especially for things like mobile devices that have a high resolution, but relatively underpowered graphics card or GPU, this is going to be a big problem. So if you want to address that, what you could also do is reduce the resolution of your shadow map. Well, if you do that, you'll get a lot of really blurry shadows. And so this is a common thing that you'll see even in games that go to production, is that a lot of the shadows you'll see are blurry. And not in kind of like a good high quality way, sometimes in a low resolution kind of pixelated way that's still blurry. So the image quality can kind of suffer sometimes. So the solution we'll go with today is going to fix all these problems. So what's the catch? Too good to be true, right? Right. It is too good to be true. It's it's not true. It's a fake shadow. So we're going to make like what I call a trick shadow, and it's going to be kind of like a magic trick. There's going to be certain circumstances where it looks really good, but it can only handle a very limited set of circumstances. So now let's talk about how we're going to do this, and it's going to be much simpler. Because remember, one of the things I checked is that we're going to solve this complexity problem. This is going to be much simpler. And let's start with this first premise that we began this whole thing with, okay? We're not going to follow this premise. So we'll still do this first part, but we're not going to do this part, okay? We're skipping that. We're just going to do our lighting like we did before. And then what we'll do is we'll draw a shadow on top of what we already did as far as our lighting goes. So we'll still draw extra geometry. We're not going to do a full other pass. This geometry we're drawing is going to be still part of our main render, but we are going to add some more geometry. But it's not going to be super fill intensive because this is mostly going to be vertices that we're adding to this. We're not really adding any more output pixels. So how are we going to draw the shadow on top of our scene? Well, let's draw, for hopefully the final time here, this table. And it's getting really a lot of work here. and our light source. And basically what we'll do is we'll draw this table again, but we'll project a copy of it onto the floor. We'll take not the vector that's pointing to the light, but we'll reverse that, and we'll say, what's the vector that's pointing from the light? And then we won't just stop at this table. We'll keep going down, 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 down until we hit this floor plane. And the floor plane will stop this projection. So we're still going to use projection, which is kind of the technique that's used during the shadow map, where we project to this picture plane. We're still going to project along this 2 light vector. And actually, if you come up here, if you look at all these light vectors, I mean, that almost looks like perspective, right? So it's still kind of a similar concept. It's still going to work the same way that shadows work. The catch is that we're relying on this floor plane kind of being the sole receiver of the shadow. So it's going to be a very limited technique. Now, you could expand that to say, okay, we know the geometry of this hilly region, and we're going to do all this fancy stuff with like a complex terrain or something like that. Okay, you could do that kind of stuff. We're not going to do that in this lesson. We're going to do a very simple version of this, but it's going to show how you can create the effect of a shadow without necessarily covering every single base of what the shadow would do in every use case. So let's head over to Unity and see what we can get done here. All right, so we're back in our light scene, and let's just make a couple adjustments before we move on to the trick shadow. So if we open our shader, there's a couple of things I want to do. First, we never actually used this base color that just kind of came with the template of the shader, and I think it would be useful in case we want to change like the color of the surface. Right now it's kind of just like a white surface that's just showing the shadow in light color. So let's multiply in our base color here. So that will fix that. The big oversight I had last time is that we never actually clamped this. So this is going to go negative lid amount. So we wanted to clamp this to between 0 and 1. We just never did it. So you say saturate. That will basically be a shorthand to clamp things between 0 and 1. It's a very useful HLSL feature. And actually, if we come over here, I think it actually looks a little bit worse without that negative light, because we were going into a full black color, and we had a different color at the turning point. So that's just something, file that away for later. But it was breaking in more sort of egregious ways elsewhere. So let's darken that a little bit, but just think about that. That's interesting effect there. The other thing I wanted to change was that this light position, light color, I'm not sure which exactly was breaking, but one of these has like a name collision with a global Unity shader variable. So let's just add PFX to the beginning of that and make sure that our script is sending those along the same way. And okay, the other big thing I wanted to change here, and it's not that big, but I think it would be cool to be able to turn this from a point light into a directional light. And what might be even cooler is like if you could do it smoothly. Okay, so let's add a direction here, which we'll need for when it's a directional light, and this will be for the point light. And then in the fourth component of these vectors, we're not really using it right now, so we can put the amount we want of point light or a directional. We can kind of encode that into the fourth component there. We'll get back to the script and actually send that correctly in a second, but let's just do the shader part first. So our 2 light vector is the thing that's going to be different for the directional or the point light. So we can say this is the version that's for the point light, right? And then our 2 light directional is going to be just our light direction, and it's going to be negative because the light direction is going to be facing in the forward vector of the light. And so we'll say that for our 2 light directional, and then we'll say 2 light overall is, let's normalize this again because we're going to interpolate between these two, and we might not end up with a normalized vector after our interpolation. And we'll just say this will be placed in the W component of the let's say light direction, because that'll be like our directional amount will be in the directions W component. Okay, so let's see if this compiles. Doesn't compile. We don't have a light position. Okay, so we need to go in and actually replace this with PFX. And are we missing anything else? Okay, light color we need to change, and shadow color we need to change. is that going to compile? Okay, that compiles. Now we're not actually seeing any difference because we now need to send this information over. So let's send over our direction. And we'll send transform.forward. Actually, we won't do it that way. So we'll say vector for dir to send, let's say, and then we'll just add w equals directional amount, and we need to create a directional amount, and we can make that a 0 to 1 range. Okay, and so I know this is kind of a lot of setup for this trick shadow payoff, but I think it will be worth it. So let's come back here, and if we make this a directional amount, we can see that's changing. Now, where is this light located? It's over here. And then let's start rotating this. So you can see as we're rotating in directional mode, that's going to be changing the light vector. And then if we go down to point mode, rotation doesn't have any effect, but moving the light around will. Okay, so that I think will just be cool to see with our shadow once we get the shadow working. So let's save that, and let's also save a copy as our shadow scene, and let's get to work with the trick shadow. So let's make a new shader, and we'll call it our PFX trick shadow. And let's actually just copy this over. We're going to use some of the same shader variables. So let's just copy this over to the trick shadow and make sure that this is named correctly up here. And we're not really going to use a lot of this stuff, but we'll use a couple things. So we're not going to use the light color. We will use these though. Okay, and then let's bring up our whiteboard image too. So here it is. Okay, so what we need to know basically is this to-light vector. That's the part that we're interested in with this effect. And the rest of it we can kind of get rid of. So this is where we calculate the to-light. Okay, we're not going to need this normal or lit amount. Now the color, it's just going to be the shadow color. So we can say out.color equals our shadow color, right? Because we're just drawing the shadow. And we've got our to-light vector, and we've got our world space position here. So basically what we need to do is take this world space position and then add our to-light, not our to-light, but our from-light. So we can say our from-light vector will be the negative to-light vector, okay? And so then what we need to do is figure out how much of this from-light vector we want to add in order to get down to the floor plane. Well, in order to determine what's the distance we need to travel along the y-axis to hit the floor plane, let's take our world space position. So we'll say needed distance y is our negative world space position dot y. Okay, so that will say if we're at 1 unit above the floor plane, we'll need to go down 1 unit to hit the floor. And then let's see what is the y component of this from light vector. So we'll say from light y equals our just from light y component. Okay, so basically now we need to come up with what is the multiplier that's needed to scale this vector to the exact scale that will take us down to the floor plane. And the scale is going to be whatever turns this value into this value. And so we saw last time that this whole idea of taking something from to, in this case it's not going to be using a subtraction, but it's the same idea. This time it's with division. So you can say needed mult equals needed dist y divided by from light y. And so if you just think about, like, let's say if you need something to be of length 4 and it's actually of length 2 currently, then you'd take 4 divided by 2 and you'd get 2. So that 2 would be your needed multiplier. So it's the same kind of idea, but with division or multiplication rather than addition or subtraction. Okay, so that's our needed multiplier. So now we'll take our WS pause and we'll add in our from light vector times the needed multiplier. The problem is here, before we compile this, we're setting the screen space position here, but what we need to do is we need to use this to determine our screen space position. So if we take this down here, that's not going to solve it because we're still using our object space position and we're going all the way from object space to clip space. So what we want to do instead is let's use this idea of multiplying in a matrix, and we'll just specify what matrix we're looking for, and we'll use this WS pause rather than the object space position. Okay, so let's open up the Unity documentation, and I'll link to this again in this video description. So what we want is this matrix VP. That's going to take the view times projection matrix, and it's not going to include this model, which is going to take us from object space to world space. We'll skip that. So we're already in world space. We just need this view projection matrix. So let's put that there. Okay, so I think that about covers everything. So let's come back here. Okay, we're not seeing anything because we don't have the geometry in the scene that's needed for that trick shadow. So let's copy our pawn and put it under itself, and we'll call this pawn shadow. And let's create a material to draw our trick shadow. So let's go into materials, and we can just copy this. We'll call this trick shadow. Let's drag our trick shadow shader onto it, and let's add that. Oh, that was cool. I think this light must be in point light mode because I'm seeing it's a very distorted shadow there. And that's telling me that like the top of this pawn is getting a very different vector that's projecting it down versus the bottom of the pawn. So if we go into the directional mode, we can see that that kind of reduces that distortion. And so now if we start rotating this around, we'll see that our shadow is following the way we have our light set up. And so then we can smoothly kind of go between this directional light mode and point light mode. And unlike in shadow mapping, where a point light shadow is much more expensive to render than a directional light shadow, in our method, you're rendering it the exact same way. So it's the same cost. Let's also see what it looks like with a different color shadow. So we can come in here, change this to red, and we'll see that this is going to render with the same shadow color that we're doing our lighting calculation. We're going to draw our trick shadow using that same color. So if we make this kind of more of like a purple color, and we can make this sort of like an orangey light color. Okay, I mean, I don't know if I recommend this palette, but we're seeing that this is working correctly. All right, so that's it for this lesson, and that's also it for Unit 1. So to mark the occasion, I put together a little demo scene that showcases not just the trick shadow we just made, but obviously the light, the parametric modeling we did, and even the quad we made in the first lesson. I kind of snuck that in as this square that gets repeated on this chessboard. So, and then you can see here over here the script that I used to make this is a couple hundred lines, but I mean it basically just uses the ingredients that we've already put together for this unit. And it also kind of serves as a preview of where we're going to go next, right? There's animation happening here, there's simulation happening here. It's happening on the CPU side, and it uses like Unity physics. But those are topics that we're going to be diving into as this course progresses. And the next thing we're going to be doing is animation in Unit 2. But we'll be doing this all in the GPU using shaders. So I'm really excited to get into vertex animation. I hope you are too, and I hope to see you in Unit 2.